So hello everyone, so I'm Dr. Murari Mandal. Welcome to Introduction to Large Language Models course. I'm an assistant professor at KIT Bhubaneswar, and today is the first class of this course, and these are the course instructors, myself, Devdev, Akash, Umakanta and Arka. And we have created a website for this course. You can go there. All the materials related to this course, PPTs, reading materials, papers, book references, source code for practical sessions will be made available in the course website. And this course is being offered by the RespAI Research Lab, which is led by myself. There are some students, so this is a teacher-student collaboration, and we are offering this course in a voluntary basis. Okay, so we hope it will be useful to all of you. So some acknowledgements. So we have also referred to many existing books, courses and blogs and YouTube for preparing these PPTs. So we have given the corresponding references accordingly. Okay, so importance of language. Chimpanzee, if you notice, it is able to correctly memorize the order of these numbers. So it is shown a number 1, 2, 3, 4, 5, 6, 7, 8 in some random order. It is able to remember that order of numbers, and it is able to click on the corresponding 1, 2, 3, 4, 5, 6, 7, 8 order. But we as a human do not have such high level of short-term memory. Right? We have comparatively to the chimpanzee, we have less amount of or less level of short-term memory with us. Right? So there is this cognitive trade-off hypothesis that our human brain has limited resources. Improvement in one cognitive area may come at the expense of other. So we as a human are very good at communicating through languages, and that is not available with chimpanzees. Chimpanzees have very high memory power. Okay, so very high short-term memory. We as a human have comparatively much lower short-term memory. But what is the advantage is we have very high, we have over the period of like many thousands of years, we have evolved the languages. Varieties of languages are out there, but each and every languages are potent enough to convey very complex thoughts, very complex arguments across to other person. Right? So that is what separates humans. This is one of the very important aspects of humans that separates us from other living entities. Okay. So what is a language model? So in language model computes a probability of each word in a sequence. So language, any language, has a particular sequence. So it makes sense when it is put in a particular order. And language model is determining how likely each word is given the previous context. So we'll take an example. So we have these 6 sentences. Jane went to store, Jane went to the store, store to Jane went the, and so on. So which of this sentence is most likely to be a correct or more probably a correct sentence? Any guesses? So Jane went to the store seems like a quite accurate, grammatically accurate sentence. Store to Jane went the, not so much. Jane went to the store, again it's all right. Jane goed to the store, so there is a like spelling mistake itself, G-O-E-D, right, which doesn't make any sense. So what is the probability of any of these sentences? Can I get the probability of sentence 1? Can I get the probability of sentence 2, sentence 3, sentence 4 and so on? So a language model predicts the probability of any textual components. It can be a word, it can be a sentence, it can be a letter and so on. So usually what we have is, any language, we have a set of vocabulary, right, that we used in formation of our sentences, during speech, during writing and so on. So when we talk of language model, we also have a vocabulary with us. So based on that vocabulary, we try to find out the probability of any sentence. So let's see. If this is our vocabulary, right? Jane went to the, so one is capital, one is small t. So language models also make differences between capital and small letters. So based on this vocabulary, we can calculate the probability of each sentence. So after calculating the probabilities, so we see that some have higher value, some have lower value, some have zero probability. So Jane GOED to the store has zero probability. That is, there is unlikely that this kind of sentence to be correct. And Jane went store has a relatively higher probability. That means it is more likely to be a correct sentence. And the first also relatively higher probability. So you may wonder, like it's 10 to the power minus 5 and so on. So we'll see. So these are actually this happens when we have bigger vocabulary. We get very small probability values. So we work with those probability values as well. So another sentence. So how are you this evening? Has your house ever been burgled? So is this a correct sentence? Reasonably correct, reasonably grammatically correct sentence, right? And it has a, depending on whatever vocabulary we are using, it has a probability of 10 to the power minus 15, like very low probability. How are you this evening? Fine, thanks. How about you? This is also a reasonably correct sentence, right? So again, depending on what vocabulary we have used, we have certain probabilities. So the task of a language model is to find out the probability of any sentence, how likely that sentence is going to be a correct sentence. Okay. So how do you find out this probability? So text is a sequence of symbols. If it's a word, then it's a sequence of letters. If it's a sentence, it's a sequence of words separated with space, comma, hyphen, and so many other symbols. So we want to find out this probability of a sequence of words or sequence of letters. Usually we will call this as sequence of words. Okay. So how do we find out this probability? So there is a Markov assumption to find out this probability, that the probability of current word depends on the probability of all the previous words, because a language is a sequence, and usually when we talk of English, it's left to right sequence. So if I'm talking about the second word, it is the probability of second word occurring depends a lot on the previous word. And if I'm talking about the third word, the probability of third word occurring depends a lot on the last two words, and so on, right? So now you see this formulation. So what we are doing is, we want to find out the probability of xi based on all the previous events that has happened before that word. So this looks familiar. This is actually Bayesian formation. Okay. So again, to generalize it, a language model is to find out the probability of any word given the probability of all the previous word before that. Okay. So a cat sat on a, it could be mad, because in the vocabulary there can be thousands of different words that are probable to appear after this cat sat on a dash. Okay. So the language model's task is to find out which word has the highest likelihood to appear after this sequence of words. So that is what the problem formulation that we are trying to solve here. So usually the language models do not deal with words. It actually deals with tokens. So what is token? Detailed version we'll discuss later, but very briefly, we actually convert the sequence of words into tokens. So this is a very simple tokenization example. So this is word level tokenization. So we just create tokens of individual words. Okay. This, after space, after every space, whatever sequence of letters are there, we just put them as a one token. Okay. So in this example, tokenization example, if we are going with word level tokenization, I have 2 tokens. There is another type of tokenization called sub-word tokenization, where we further divide this word into sub elements. So for example, this we'll discuss in more detail later. Tokenization is actually made up of 2 subwords. One is token, another is ization. So if we go with subword tokenization, we get 3 tokens. So actually language models deal with tokens and not words directly. So again, but the problem still remains same. Given a set of tokens, what is the probability of next token? Okay. Instead of words, that I gave the first example, it's easy to understand, but same logic you can apply at token level. So another example, the students open their, so what would be the next word? Books, laptops, exams, minds, and so on. So the question is, how many such words are there? Depends on your vocabulary size. So depending on how bigger vocabulary you have, so if there are 1000 words in the vocabulary, you have to calculate the probability of each and every one of those words and then select the word that has the highest probability. So at each time step, sample a token from the LLM's new probability distribution over the next token. So because again the language is a sequence data, so we actually start with the first word. If we want to predict the, let's say the goal is to predict what word should be here, right? So we start from the beginning. What is the possibility of students after the? What is the probability of opened after the students? What is the probability of there after the students opened? So like this we calculate this probability, and at the end we can also find out the probability for the last word that was the original problem. So in short, language models can generate text or next tokens. So how it does it? So we usually have a very large corpus. So this corpus is actually, we have lots of well-written paragraphs, well-written books, documents, from where the language model will learn how a grammatically correct sentence looks like, or how a semantically correct sentence looks like, or how meaningful information appears like, right? So we create a very large corpus. So that is what you keep hearing, like this LLMs are trained on very huge data. So that is what we're talking about, the large corpus. On those large corpus, we train our language model. Either you train or we even go for statistical methods. We'll see there are different ways to solve this problem. And after the language model has been trained on this very large corpus, we can solve a particular problem for which it was trained for. So this is one example is auto-completion. So we are discussing by default auto-completion example. We'll extend it to different other applications later on, but this is how we will keep discussing all the algorithms in terms of predicting next word. Okay. So you must have used Google search, right? So if you write in the Google search few words, it suggests you next set of sentences which are more likely to be the words that we are going to type, right? So what is large language model then? So we talked about language model. So then what is large language model? So large in this LLMs. So now we are talking about LLMs. So large implies 2 things: large model size and large data set. In this case, corpus, large corpus. So that actually usually converts into large number of tokens. Okay? And in terms of model, it becomes the parameter size of the model. So we'll discuss this more detail. So right now, we just assume that models have a set of parameters that are defined by us only, and we can have as big model as small model as we plan to. So some of the models that are out there currently, we have llamas. Llamas have series 7 billion, 13 billion, 70 billion, and so on, 405 billion. GPT, I think GPT-2 was 175 billion, GPT-3, I don't recall, but GPT-4 is presumed to be 1.7 trillion MOE, which is mixture of expert. We'll discuss that later. But this is a guess because GPT-4 is actually closed model, so the information is actually not available. So this is from the whatever is out there in the Reddit and so on. But the idea is, so Palm 2 is from Google, Ernie is from Baidu, they have Gemini from Google and so on. So these are all very huge models if you notice it. So then we have some more. Grok 1 was 33 billion. We have Falcon 180 billion. So this 180 billion, this 300 billion, 400 billion, these are billion of parameters. These parameters are with respect to the models, and the number of tokens is with respect to the data set. Okay. Yeah. So there are many open source corpus available. The companies who train their model on what data they don't reveal usually, but there are open source data set available. Anyone can use it. So we have up to 1.6 TB, 800 GB, 2 TB. So quite large data sets are also available nowadays for you to train your own large language model as well. This is some more summarization of different models by Anthropic, Google, OpenAI, and so on. So, so where does large language model fits into the overall AI landscape? Because we have machine learning, we have deep learning, we have generative image models like diffusion models and so on, and the AI. Okay, so which is the kind of overall umbrella under which we are studying all these directions. So the bigger kind of domain is AI, artificial intelligence, and then inside AI. Machine learning are a set of algorithms that help us learn from the data, and deep learning is a special type of machine learning algorithm. So deep learning becomes a subset of machine learning, and computer vision and NLP, these are two major domains because of two major categories of data that we have available with us. One type of data is textual data, another type of data is image and video data. Almost everything is either text or image, right? So for image or video, we have computer vision as a domain. For text, language, speech, we have NLP. And both NLP and computer vision problems can be solved through machine learning algorithms, through deep learning algorithms, and right now we are in the phase of generative AI. So generative AI, again you can think of two subdivisions. One is for generative images, another is generative text. So LLM is generative text, and diffusion models and GAN, so these are all generative images. Okay. So that's why generative AI and LLMs fit into somewhere here. So if you want to have a different perspective on this, so this is how AI, machine learning, deep learning. Inside that we have LLM. So LLM is actually one part of Gen AI, which is more focused on text, and then another part is diffusion models and all, which are more focused on image. So where do we use language models? So we use language models. We have been using language models, the applications based on language models for at least past 20 years, 20, 30 years. Only thing is now it's becoming more popular because of the increase in capabilities that are available with us based on these language models, okay. Particularly ChatGPT, since ChatGPT. So we have autocomplete in our mobiles, right? We type something, it suggests. Google's, we have chatbots. We have much better chatbots now, powered with LLMs, but it was there even before LLMs, okay? Although they were not that useful, but it was there, right? So question answering basically. You can ask some question, it can answer. So, translation, English to Hindi, any language translation. So this again becomes a language model problem, okay? Code generation. So code generation is becoming more and more powerful, particularly powered with the LLMs that we have. So if you think about it, code generation is also like text generation problem, right? You ask a question, and the language model has to understand the question and generate a set of text for it, which are in this case a code. Recommendations. Recommendation again, we have been doing recommendation without language models, with language models, and different types of recommendations, but they have become much better with the support of large language models. Okay, so code generation. Writing assistant. So this is again a very nice feature, I think very super useful. You can describe some concept in a kind of very unorganized manner, and the LLM can generate a very nicely summarized or very detailed description of that ideas that we are looking for. So basically there are many other applications. So you are already using ChatGPTs, Gemini and so on. And the idea is it's not just next, although at the core of language model is text generation, but that itself is so powerful, it can support so many wonderful applications. Okay? And we'll see some of them in the discussion of this course. So evolution of language models / large language models, because it's basically language model. Only thing is we have increased the parameter size, we have increased the data set size. Everything else remains the same, right? So language, computational approach to languages, to work with languages, to develop language model is nothing new. Scientists are trying this for very long actually. So since 1950s, people have started working on how to enable computational algorithmic based language generation, language prediction, and so on, right? Question answer and so on. So early methods, so the difference is the approach to solve the problem. So early methods used a lot of rule-based approaches. This applies to actually pretty much all the applications. Even computer vision, early approaches were rule-based. Even NLP, early approaches were rule-based. So what are rule-based approaches? We'll see some example in the subsequent slides. The late 80s, 1980s and 2000, we started with a statistical approach to NLP. So lots of probability and statistical methods were employed to solve the same problems that we are solving right now with neural networks and deep learning and so on. And some of the popular methods were like Markov models, hidden Markov models, bag of TD-IDF, and then some neural networks as well, like RNNs, LSTM, and so on. So this was till early 2000s, maybe 2005, 6, or 7 also. So around 2009 or 10, the new phenomenon of deep learning started picking up, particularly due to the AlexNet paper, although it was from image side. Okay, so AlexNet is a computational neural network method which was proposed to solve image classification problem on very large data set, ImageNet data set. But the idea was that if you increase the number of layers in a neural network, it substantially improves the capability of the neural network, so that it can solve much complex problem with much better accuracy. So those ideas were also incorporated into NLP side as well. So then we started having some ideas which are deep learning based natural language processing ideas. So some of the major milestone in that was word-to-vec, sequence-to-sequence models, and of course now we'll reach to the seminal work by Google, attention is all you need, which is the transformer model. So transformer model is one type of neural network model, but before that also we had some other types of neural network model to solve this language modeling problems. So since 2007, so the first paper of the transformer was in 2007, which was by Google, attention is all you need, so which is the transformer model, 2017, So since then, of course, there were some parallel methods, so I think we'll discuss them later. Okay, so there were some other methods also. Google it also came up with BERT, so that was also a slightly different architecture, but also quite powerful. And then since then, we have a lot of different architectures. Pretty much all are based on transformers. So we have Gemini, we have Claude, we have Llamas, we have Quen, we have DeepSeek. So these are all transformers based architectures with slight variation here and there. And if you have observed in the last 1 or 2 years, the scale is increasing. The scale of the data set, the scale of the model size. And that scale itself is giving us lots of newer and newer degrees of performance to solve more and more complex problems. So this is really interesting, and more details will be discussed when we come to the transformer topic, why it works so well with the scale, how and why, all those things. So coming back to our language models. So how do we build a language model? So we have corpus, we have some model. Our goal is to build a language model using that corpus to solve certain language-based problems. Currently we are discussing next word prediction. So first is we collect a textual corpus. The corpus should be diverse, it should be clean, it should be grammatically correct. So there are lots of effort that is required to collect the correct textual corpus as well. So if your data is not good, your model will perform poorly, right? Irrespective of what approach you use to build your model, right? Deep learning, transformer, whatever. So once we have this corpus, find a distribution that maximizes the probability of the corpus. So all these methods are actually, this learning based methods are doing this only. They are doing maximum likelihood estimation. So they are trying to find out the distribution, kind of correct distribution of the corpus, which can help us identify the most probable next token or next word. How do we do that? We'll see. So if we do not train a language model, by default it will give out garbage. Okay. So the idea is to show it some nice corpus and guide it towards making correct predictions or correct generation. So something like this we want, right? So we want the language model to develop, to produce a coherent sentence, semantically meaningful sentence. It should be useful to the purpose for which we have trained, built the model, and so on. So Ohio is a state in the contiguous United States of America. So this is a well-formed sentence, right? Grammatically correct, and so on. So early rule-based methods. So this is now we are discussing some of the sample algorithms. There are many other rule-based methods. So we are not going to discuss much detail those algorithms. So earlier rule-based method was if-else kind of setup, right? So if Ohio is in the prompt, print Ohio is a state in the contiguous United States of America. Else print I don't know. So this is very basic if-else kind of algorithms, which really are not useful. But these were earlier, ideas. So 1970s, researchers started coming up with statistical based methods. So statistical based method is from the corpus, identify some the probability distribution of these word sequences, okay, and based on that probability distribution, identify the most likely next word or next token for a given sentence. So like we had the n-gram models is a popular one, so we'll discuss n-gram model, how it works and so on. So in statistical methods, one naive solution is assume that we have n training sentences. So and let x1, x2, xn be a sentence. So these are words, first word, second word, third word, and the last word in a sentence. And what I need to do is I need to find out the probability of this sentence, okay, whether this is a correctly formed sentence or not. So one way to find out this probability is in the corpus, you find out if there is already this sentence available in the corpus or not. And you identify how many number of times in the corpus the same sentence appeared. Because if in the corpus this sentence appeared somewhere, then it must be a correct sentence or correctly formed sentence. Otherwise not. So you count the instances of this sentence in the corpus and divide it with the total number of sentences in the corpus. And you get some values, so that will be your likelihood value. So based on this, you predict whether this is a correctly formed sentence or not. Of course, this is a very primitive approach, and this will most cases fail, and it will not generalize also, because if something is not there in my training data set, this model will fail to answer in that scenario. So next is we will discuss n-gram models. So before that, the Markov assumption. The Markov assumption is, for a given sequence of words, the Markov assumption says that xt plus 1 depends only on the preceding n minus 1 words. So if I have x1, x2, x3, x4, x5, x6, the probability of x6 depends on the probability before x6, that is x1, x2, x3, x4, x5. So this is called Markov assumptions. So the thing is, if the sentence is very long, or even a short sentence, and I need to find out the probability of p of xt plus 1, that is word at a particular position, I need to find out the probability of all the words before that position, and then I need to find out this probability. So there is some more simplification of this Markov assumption, that okay, instead of looking for all the n minus words before the current position word, can I just look at the one word before, or can I just look at 2 words before, or can I just look at 3 words before and try to estimate the probability of the current word. So those relaxation of Markov assumption led to different n-gram solutions. So that is called unigram, bigram, trigram, and so on. So like for example this one, I want to find out what is the next word. Okay, so its water is so transparent that, what should be the next word? So I am finding out what is the likelihood that the will be the next word after this sentence. So if I go with the full Markov assumption, I need to find out what is the probability of its, what is the probability of water, what is the probability of is so transparent and that, in order to find out this probability. But the relaxation if in Markov assumption says that, why not just look at the probability of transparent that means previous 2 sentences, previous 2 words, or maybe even just look at the one word before. So this actually is unigram, this is actually bigram. So an example is here. So this is general description of n-gram. So let's say I want to find out the probability of any word given a sequence of words. I need to actually find out the probability of all the previous words, n minus 1 words. So that would be n-gram. If I relax this condition and just calculate the probability of one word before, that becomes unigram probability. So how it works is, let's say this is a sentence. I have a dog whose name is Lucy. I have 2 cats and they like playing with Lucy. So if nothing else is given, okay, if nothing else is given, this is the only information I have with me. So this is actually becomes my corpus. Okay. So what is the corpus size? I need to find out the unique words or symbols in this sentence. So it turns out there are total 17 unique words or symbols. So even we include this also, okay, the quote and dot, okay, full stop and all those things. So if you look at, there are actually a comma also will be part of the corpus size. Okay. So we have total 17 corpus sizes. So basically these are 17 tokens actually. Okay. And I will find out the probability of each words in this corpus. So if the total corpus size is 17, so what is the probability of Lucy? So total number of times Lucy has occurred in this corpus divided by the total corpus size. Total corpus size is 17, and how many times Lucy has occurred? 2 times. So probability of Lucy will be 2 by 17. So likewise I will calculate the probability of each and every word in this sentence. Okay. Probability of cats 1 by 17 because cats appeared 1 time, and total corpus size is 17. So like that I calculate all the probability of each and every word. So fine, so PW is equal to count of W divided by N, and M is the corpus size. So what was our original goal? Original goal was to calculate the probability of the entire sentence. So the probability of the entire sentence, which is a sequence of words W1, W2, W3, so this becomes W1, W2, W3 and so on, Wn is equal to probability of W1 multiplied with probability of W2 multiplied with probability of W3 and so on. So after doing all this multiplication of the individual probability of each and every word, we get the total probability of this sentence. So this approach of finding the probability of a sentence is called unigram based probability. Fine. Similarly, we can go for bigram probability. So bigram probability is the probability of the current word depends on the immediate previous word. Remember, we are still working with the Markov assumption. So in unigram probability, we said that the probability of the current word doesn't depend on any other words. These are independent events, right? So then we got some probability of the sentence. Now I am assuming that the probability of the current word depends on the immediately previous word. So then the probability becomes probability of the entire sentence becomes like this. At any position in the sentence, the probability of that word will depend on the probability of the previous one. So something like this. Probability of have will be probability of have given I. Probability of A will be probability of A given have. Probability of dog will be probability of dog given A, and so on. Now, how to calculate that probability? We'll again go for Bayesian principle, Bayesian theorem. So basically, what is probability of A given B is equal to probability of A comma B divided by probability of B. So this is from Bayesian theory. So what I need to calculate is, I need to calculate probability of have given I. So for this I need to find out what is the probability of I have. So I need to find out the number of occurrences of I have in this corpus. So how many times I have has occurred in this corpus? 1 and 2. So this will become 2. And what is the probability of I? How many times I has occurred? 1, 2. So 2 by 2. So probability of have given I is 1. So let's look at some other example. Probability of 2 given have. We are calculating this one. Probability of 2 given have. This becomes probability of have 2 divided by probability of have. So probability of have 2 is find out how many times have 2 has occurred. Have A, have 2 has occurred 1 time. So 1 divided by how many number of times have has occurred? 1, 2. So 1 by 2. The probability of 2 given have becomes 0.5. So like that I will calculate all the probabilities in this sentence. So these are my bigram probabilities. The probability of the current word depends on the probability of the immediately previous word. Or you can think of tokens. So I will use the word because it's easy to understand. But in actuality, we actually convert into tokens and then work with tokens. So after I have calculated all these bigram probabilities at each and every position in this sentence, how do I calculate the final probability? Final probability will be multiplication of all these probabilities. Okay, and then I will get the overall probability of this entire sentence. So again, and then we'll threshold. If it is higher than certain threshold, then we'll say this is a correctly formed sentence, otherwise not. Same principle we can apply for. So this is an example. I will leave it. I will not discuss this. You can solve it on your own later. Similar principle we can apply for trigram probabilities. So in trigram probabilities, the current word's probability depends on the last 2 words, immediate past 2 words. Okay. So it will be, so this is an example. So probability of W3 depends on W1 and W2. So again you apply your Bayesian principle and again you can get a formulation of it. You solve it, calculate the trigram probability of each and every token or word in the sentence, multiply them, that is the overall probability of the sentence. So this you can actually expand as much as you want. You can create 4 gram probability, you can go for 5 gram. So, and like that we have any value of n you can select and you can calculate the probability of the sentence. What is the difference? Which one is better? We'll see an example. So this is the result of 1 gram probability based sentence formulation. So I get sentence like Hill, he, late, speaks. This is a kind of, this is garbage basically. Why? Because the sequence, the word that was chosen to form that sentence was not dependent on any other words. So these are just random collection of high probability of words from the corpus, right? So they don't make any sense. Let's go for, let's check out this 2 gram, bigram based sentence formulation. What means, sir, I confess she. So this looks slightly better than 1 unigram. Right? Let's go for 3 trigram and 4 gram. If you look at the 4 gram, right? King Henry, what? I will go seek the traitor, Gloucester. And this is much, much better. Right? So as we increase the number of words based on which we are calculating the probability of the current word, we observe a very better semantically meaningful sentence formation or grammatically correct sentence formation. So this is one type of language model. So these n-grams are actually one type of language model. So they are helping you create, they're helping you find out the probability of the next word for a given sequence of words. So these are one of the simplest statistical language models. There are much more advanced ones, so we will discuss this later. But this is one example of a statistical based language model which was very prevalent. Even we use it now also for very simple language modeling tasks in language NLP. So next phase which started around 90s, particularly with RNN and LSTMs. With the advent of RNN and LSTMs, which could model sequence data within a neural network framework. So here, instead of looking at the statistical distribution or trying to find out the probability based on the corpus data, we actually train a neural network using the corpus data. Okay. So the thing is, to train using a neural network, I need to create some labels. So that was one of the biggest bottleneck of neural network based language modeling, that I had to create those corresponding ground truth labels. Okay, what should be the output, right? That I have to give to the model, then only it learns well. But yeah, so there was a lot of advancements in neural networks that ultimately led us to transformers. So we'll go through all those early neural network based solutions like RNNs, LSTMs, and word2vec and all those things, and then we'll come to transformers in our subsequent lectures. But the basic idea is this. So we have a neural network, okay? And the goal is to train the neural network to find out the distribution of the vocabulary so that it can correctly predict the next word. So something like this. So Ohio is, this will be taken as input by the neural network, and then the neural network will try to predict what will be the next word, right? And so on, right? So this becomes the task of the neural network to predict the next word. How we train it and what are the methodologies, we'll discuss in more detail later. So this was till 2016-17. Different varieties of these LSTMs, RNN, GRU, and many other neural network based methods that were proposed. One of them is actually transformers, and that changed the whole game. Okay, so transformer is not this transformer and not even that transformer, because these are all transformers. So we are talking about this transformer. Okay, so this is actually the framework proposed in the Attention is All You Need paper. Okay, so whenever we are talking about transformer here, so we are always talking about this one. again, very basic. So transformers, BERT and GPTs, they were the earlier transformer-based methods. So they proposed two-stage pre-trained models. So that was not the norm before. Okay, so that was like one of the major kind of contribution, that we could solve the problem in this way as well. Okay, and that transformed the whole game of NLP. Particularly, we went from specialist specialist language models to generalist language models, which could solve all the problems, all types of NLP problems. Whereas previously we were building more application-specific language models. So one language model can solve only one type of language problems. One can do translation only, one can do next word prediction only, one can do recommendation only, and so on. But these transformer-based models, BERT was the earlier one, and GPTs, they can actually perform all types of NLP tasks just by the single model. So that was the one really amazing thing that happened. And yeah, so we are actually currently living in the age of transformers. Okay. So, and how this whole thing happened and how it is changing the landscape of AI, the field of AI itself and many other applications. So let's go through the history of this, how it all happened. The first paper dropped in 2017. Attention is all you need. The authors were all from Google. So what they did was, they proposed a transformer and use it for a language representation, as a language representation models. So how and why, that we'll see later. Subsequently, actually what happened was, although the paper was, the first transformer was proposed by the authors of Google, they were actually late into scaling it up. So OpenAI actually picked up the idea, and they actually started scaling it up. Okay, so they started coming with GPT-1, GPT-2, GPT-3. Of course, Google did catch up later, but the earlier kind of breakthrough, breakthrough level of kind of performance were shown by the OpenAI paper. Okay, so that was the first GPT paper. So they showed a decoder-only transformer architecture, kind of variation from the BERT architecture that Google has. And this left-right context, all these things we'll discuss later. So at the similar time, so that's why if you notice the red boxes, so these are the date or the month and year on which this paper dropped. Okay, so July 2017, this was the attention is all you need paper. June 2018, this is GPT-1 paper, and October 2018, this is BERT paper. So they also tried to Google also tried to kind of scale up, but with different approach. So they went with encoder-only transform architecture, whereas GPT was decoder-only transform architecture. So now all the models are actually decoder-only type. Okay, because that is giving much better performance than BERT style of architectures. And the second thing what these OpenAI people started doing is, they started scaling up the model. They just kept stacking up the transformer layers, okay, one after another. So GPT-1 was 117 million parameters model. GPT-2 was 1.5 billion parameters. Okay. And there was not a lot of architectural changes, to be honest. So that will be discussed later, like how and why. And yeah, but they kept increasing the model size, and they kept increasing the corpora size, or like the number of tokens that were used to pre-train and all those things. And then GPT-3, which actually then launched their first product, which was ChatGPT, right? So it was based on GPT-3. So that was 175 billion parameters. So this was huge at the time. So no one could even imagine that we could even try to train such model. See, the equipments to train was available, but no one could even thought of that just by scaling up we could achieve such a huge boost in performance, right? So that is what OpenAI did. Okay. So, but nowadays, every other day we see a new LLM model dropping, right? So how many transformers are out there? So many, right? So we can't even keep up, right? So there is Llama series, there is Qwen series, there is DeepSeek series, there is Mistral is there, and what else? Like Grok is there, right? Flan, and then Falcon, so Coachella and Alammar, and like so many, like Tulu, and like so the number of GPT transformer models out there are huge, and there is not much difference between them. Okay, these are all transformer models. Okay, so don't have to get confused like what is this, what is that. Everything is actually transformers. Only thing is some small tricks, some data set cleaning, some specific data set they had, and some tricks they are using to improve the performance on certain aspects, some math based problems, some reasoning problems, some coding problems, and so on, right? So we are currently living in the age of transformers, and every one of us should be aware what transformer is, what it can do, how to work with it, how to play with it. So that's what this course is about. Okay. Yeah, so ChatGPT launched on November 2022, right? And that led to so many similar other LLM based models, right? So we have Gemini, we have Claude from Anthropic, we have Meta, and so on. So what is happening currently is these transformer based models, so they are currently outperforming even humans in many of the tasks. Complex problem comprehensions, math problem solving, coding, what else? Summarization, English, essay writing, and so on. Like, so almost whatever problems that we are able to think of, which are based on language or based on text, all the models currently are able to perform better than humans. So this is really, really interesting, and this is a really kind of pivotal moment in the whole advancement of evolution of AI, because this has never happened in the last 75 years of AI research. Okay, so AI started around 1950s, and now we are almost 75 years, right? So this has never happened, that AI models are outperforming human-based solutions, not everywhere, but almost whatever problem currently we are able to think of. Okay. Only thing is, challenge currently is we are unable to come up with ideas how to evaluate these models better. So that is a very big challenge. We'll discuss that later. Right? How to evaluate these models, because whatever evaluation mechanism we are able to think of, they are able to perform very nicely, better than humans. So what is next? So coming back to this course. So what this course is about, and what you will learn in this course, how it will benefit you, and what you can expect at the end of this course. So one is comprehensive LLM journey. So we'll start from the very basics of NLP, and we'll cover almost 60-70% of the NLP topics, which are non-deep learning, non-LLMs. Then we'll move on to deep learning, and then we'll move on to LLMs. In LLM, we'll go as much as possible. We'll try to cover as many aspects as possible. So it will be a full comprehensive journey for you in the space of LLMs, okay, this course. Industry alignment, learn methods and tools that are widely used in the industry. So we will be discussing some of those open source models, how to play around with it, how to fine tune it, how to optimize them, okay, how to work with them, and some RL optimization on top of those models. So which is industry also doing the same kind of stuff to solve their industry relevant problems. So skill enhancement, you will get hands-on experience. One part will be this classes, another part will be the practical sessions. So you'll also get hands-on experience also, how to actually code up, how to actually train, test, all those things. It's important to understand the history, background behind LLMs. It's not just one shiny thing that happened last 2 years. It's the effort of last 60-70 years of different levels of advancements by researchers. It's important to understand those contexts, otherwise you may not get the full picture of why they work, why they don't work. Okay? And we'll provide the context, we'll work with the current trends, and of course we will be talking about the core NLP concepts, which will also build a sound theoretical foundation for you, because if we just talk of LLM, these are just transformers, right? So there are a lot of other things beyond transformers. So that is also important to know. Real world applications, we will also show some real world applications using these models. Some text classification, sentiment analysis, maths problem, coding generation, all those things. So some code learnings would be understand different architectures, including transformers, of course, RNN, CNN, LSTMs, word2vec. So these are some of the foundational principles of language modeling. So that also will be discussed. Neural networks, backpropagation, building a language model from the scratch. So all those things will be covered in this course. And also how to train, how to test, how to set up the environment, coding side. So those things also will be discussed. On transformers, we'll go very deep. We'll start from very simple concept, then we'll keep building on top of it. We'll train this transformer, we'll test it, we'll discuss the auxiliary kind of support like RAGs and these different optimization methods, PPO, DPO, GRPOs, and different tokenization methods. So there are, for every concept, there are many methods to solve it, right? So we'll discuss the prominent ones in this course. And so it will really help you develop, build your mastery in this field of LLMs. So you'll get insights into how a complete pipeline of LLM works, how pre-training works, how post-training works, how to do fine-tuning, how to do in-context learning, what are agents and all those things, LLM agents and so on. So there are different types of distillation methods as well. So all those things we would try to cover as much as possible in this course. So of course this will naturally help you skill up for or make yourself future ready for the how LLM is going to change the entire industry, all kind of industry, not only software industry. Every industry is going to get impacted or like they are going to adopt these latest innovations. So naturally, if you are aware about the backgrounds, you have hands-on experience, you will be better prepared for those upcoming job opportunities. And also, if you're interested for research or entrepreneurship ventures, so this will be really helpful for you. So yeah, so this is about the course, and from next class onwards, we'll start moving to the statistical NLP and neural language modeling. Thank you.